Hello everybody and welcome back to my lab. I'm Scott Card and this is the third installment in our how-to series for Proteus. Today I want to talk to you about multiple power rails, terminals, multi-page design, and graphing. I'm starting off here. I have a blank slate. You'll notice that I didn't use the template. It really doesn't matter today because we're going to talk about power rails first. And so the first question that I'm usually asked about this is, why would I want multiple power rails? And my quick answer to that is, very often with today's electronics, we have multiple power rails for different devices. And so, for example, a microprocessor may have separate power rails for the logic, for the analog, and possibly for some high voltage outputs. And so, we quite often need these different power levels. And so, let's start off. I'm just going to press P here and pull up my my menu to pick some parts, and I'm going to pick a random part. Let's pick a SIL 156 and say a 5-pin. Good enough. This is just going to give us somewhere to connect our power rails. And so over here in terminal mode, this is a great place to start. And you'll notice that there are a bunch of different terminals that we can pick. And so we're going to start off by just picking a plain old power connector. And I'll connect it here to pin 1. And if I grab another one and connect it to pin 2, we will find that if we go to our PCB and layout J1, that it wants to connect pin 1 and pin 2, which it shouldn't be a surprise. These are both power. So let's go in, and now we're going to change this a little bit. I'm going to take these and I'm going to change this. I'm going to change this one to 5V. I'm going to actually label this, and this one I'm going to label 3.3V. And the idea is that I have these two powers that I want to bring in or take off of my circuit board. And when I go to PCB layout, now I'm going to get an error. And you see it says that there's a net list error. And if we click on it, it'll tell us that there's no power supply specified in the power rail configuration. And so this is perfect. This is exactly what we want to see. And so the way that we're going to correct this is to set up our power rails. And we do that by going to Design, Configure Power Rails. And you'll see that there's two power rails here that haven't really been defined. And so this first one, we can actually connect this one to VCC. VCC, you see, is already set for 5 volts. We'll add that one, and we'll call it a good enough. Okay. And then we can go back in and do this again. And this time we have this 3.3. We need to connect it somewhere. So we're going to create a new power supply, and we'll call this one 3.3. And you'll notice that it's clever enough to figure out that this is 3.3 volts. And now we're going to connect 3.3V to this. And now when we go back to our PCB layout, there's no errors, and pin 1 and pin 2 are not actually connected. And so that's fantastic. Now let's grab another component here. Let's pick something that has our VCC and ground already connected to it. Something like a PIC 12F. Here we'll do a super simple one. 10F 100. No. 10F 22. Perfect. 222. There we go. And so the first thing to bring up to you is you'll notice that there are 4 pins here, but there's 8 here. And so it's kind of odd thing that you should notice right away. And so here we go. I'm going to connect this in here and we're going to call that good. We're going to come back here and we're going to place that U1. And notice that it actually wants to connect pin 2 to pin 1. It's actually figured out. It knows that this ground pin is connected to VCC. Let's argue for a second that we don't want this connected to VCC. We want it connected to our 3.3. And the way to do this is we're actually going to go into our edit properties and we're going to go to hidden pins. And in this case, instead of connected to VDD, we can connect it to 3.3. Then we'll say, okay, we'll go back to our PCB layout and it didn't work. Let's see, netlist errors. Okay, so there is no 3.3, so we need to try this one more time because it's called 3.3V, right? Hidden pins. Okay. Perfect. This time it worked. Which brings up a fantastic point, which is we have to be really careful with the labeling in our terminals and our power rails. And so now we actually have something connected to our pin. And so this is great. This is exactly what we need. And so let's grab another thing on here. Let's grab a ground. And now you can have multiple grounds as well. Grounds will need to be separated from time to time. For example, if you have an analog ground and a digital ground, you may all want to all have them set at 0 volts, but they're definitely different things, okay? For example, we'll call this one A-GND. Maybe this is an analog ground, and it's not the same as the other ground. So we'll go back in, design, power rails. Notice there's an analog ground, so we'll create a new one, and we'll call this learn to spell analog -G. Perfect. Notice it's 0 volts, and we'll add this to it. When we go back to our PCB, notice it's not trying to connect our ground to our pin. You may want to have actually something in here though. So let's grab another ground like this. And I'll grab a resistor. Perfect. And we'll make this 0 ohm. Incidentally, 0 won't be happy in here, but you can put in shunt. So now I have a shunt resistor between the analog ground and the digital ground. And when I go back to my PCB layout and I drop in my little shunt resistor, again, plus and minus, a great way to rotate. So now I have a shunt resistor to isolate my analog ground from my digital ground. And so this is again is perfect. Okay, so the next thing that we wanted to talk about was terminals in general. And basically these are terminals. They just happen to be associated with power rails. But there are other types of terminals. Notice that there's a default, there's an input, there's an output. We'll rotate them around so they're the same way. There's a bi-directional. Okay. Power and ground we already talked about. Chassis ground, again, it's a thing. Okay. We've got dynamic, and we're going to worry about buses later. But I will talk to you about the no connect. No connect is great. I like to use it when I have chips that actually don't have a connection, because it tells me that I didn't forget about it. It's left blank intentionally. So these are very, very helpful. So the rest of the terminals here, let's grab another one of these. And we're going to put them up here like so. Oops. That's just horrible, isn't it? Okay. And so we have all these different terminal types. And the question is, what do we predict is going to happen when we take a look at J2? I mean, we have an input, an output, a default, a bidirectional, and dynamic. And the answer is that they are all the same, basically, right now. Okay, so we have all of our terminals. They're different types, but they're all, in essence, connected to nothing. A terminal without a label is nothing. Okay, but if we double click on them, then we can actually start to add some detail here. And so I'm going to call this one 1. I'm going to call this one 2. I'm going to call this one 3. And there's a much easier way to do this that I'll show you later. 4 and 5. Okay, so now I have these 5 terminals. And when we go to our PCB layout, again, nothing's happened. These are 5 individual things. But if I change them all to 1, there we go. They're all 1, and I go back to my PCB, it wants to join them. So what's the takeaway here? The takeaway is it doesn't matter if you're using an input, an output, a default. They're all the same. They're all connected as long as they have the same label. So where would we use this? Perhaps you wanted to use this as an input, and this is here. So we have an innie and an outie. Like so. When we go to our PCB, it's going to connect 2, which is an out, to a 2, which is a in. So if this helps you in any way to do your layout, then bless you, go for it. Okay, it really is something that you can manipulate however you wish. Just keep in mind that it is actually they are connected, regardless of the type. Okay. Now, you do want to be careful connecting these to power rails, but that's a different thing altogether. Okay. So now we have our terminals. That's fantastic. Okay. So now you've run out of space on your page. You've filled your schematic up, and you need to keep working. So what you can do is you go under Design and go down to New Root Sheet. And this opens up another page. It didn't make your page disappear. It just opened up another page. And you can always go back to your other root sheet by either going to Design and Root Sheet, or right-clicking and picking a root sheet. You can also go to Design, and under a sheet, you can rename this sheet, Edit Sheet Properties. And we can title the sheet, and this one we'll call this, just for now, we'll call it main. Okay, and we can see down here it says main, and the other one says root still. So we'll click on it, and we will go to Design, Edit Sheet Properties, and title this sheet Second. So now we have our main sheet and we have a second sheet. Let's throw in our nice silk connector again, and we will throw in a couple terminals. Okay, let's grab just the defaults. Sure. All right, and we're going to throw some labels at this. Perfect. Okay, so this schematic, we have a component and a lot of things that are connected to the other page. So what happens when we go into our schematic? Here we go. We have J3. We'll toss it in. And notice that these terminals all want to get connected the same as on the single page. So what does this mean? It means that you can continue your pages and break your circuit up into logical bite-sized pieces. For example, you could have your microprocessor on one page. You could have a power supply on another page, and everything is in a logical way broken up, but yet still part of the same design. And when you simulate, sometimes you will have some problems with this, and so this isn't the best way for simulation, but it is a great way to do your layout to make it clean and neat and easy for others to understand. The next thing that I wanted to talk to you about was graph-based simulation, and it's a very, very powerful tool. And so here I've created a very simple circuit. So I have a resistor and a capacitor, and what we're going to look at is the charge time and what it looks like when we charge a capacitor through a resistor. And so what I've done is I've set up a simple voltage source, so it's going to turn on 100 milliseconds after I start the simulation, and it has a pulse width of 99% and would take it's a millihertz. So basically, for all intents and purposes, it's just a delay on circuit. And so what we expect to see is when it turns on, this capacitor will charge up, and as the current goes down, the voltage will increase, and we'd be able to take a look at it. And so if we just run the simulation, we can see that it does actually ramp up, but it's hard to see what's happening. And the conventional thing would be to hook up an oscilloscope, and you could capture that. It's really hard to capture it. It doesn't simulate well enough. In this case, it's maybe too slow, or it could be too fast. But the transient, the event is way outside our ability to capture it with conventional methods. And so what we're going to do is we're actually going to create a chart. And so the first thing that I did was I put on some voltage probes. So I have one here and one here, and you know what? We can grab a current while we're at it so that we can look at what's happening with the current. And we'll go over here to our graph mode. And today I'm just going to show you the analog, but I'll show you some other ones later in the video. So we're just going to draw a rectangle, and this is our analog analysis. And so we're going to be looking at the voltage. And so what we're going to do is, this is a little finicky. You have to highlight it, and then you're going to grab it and pull it in. So there's C1 and R1. And we can actually go in and relabel these if we want. So we could relabel C1. So this is cap voltage. And this one is source. And there's also the ability to do some math in here as well. But we'll save that for later. And the other one that we're going to grab is our current. And I'll put it on this side. And so the idea of putting some on the left and some on the right is that we're able to have different scales. And so our start time and our stop time are okay. And we can also change things like the scale. We're ready to simulate. And so running the simulation down here isn't actually going to give us the results that we want. There's two ways. You can right click here and simulate the graph, or you can simply press the space bar and it will run the graph. Notice here that it is color coordinated. And what we have happening is our voltage at the source turns on. It's hard to see here because it exactly mirrors the current, and so our current spikes up to 100 microamps, which is basically the short circuit for the 10 kilo ohms at 5 volts. Okay, or at 1 volt, I should say. And then as the voltage in the capacitor rises, the current feeding it drops. And so the higher the voltage at the capacitor, the less potential there is, which means less current's being drawn until it actually works its way down in this asymptotic curve to near zero. Now, one could argue that there's always a little bit of current due to leakage and the diminishing return problem, but as they say in engineering, it's not just good, it's good enough. So there we go. That is a very, very powerful way to take a look at what is, once you're in third year, really simple sort of concept, but to visualize this and to actually be able to play around with these values is a great way to learn and to experiment. And so I encourage everybody that has Proteus to play with this simulation and really start to use it as a learning tool. And now, on the topic of learning tools, there are a whole bunch of designs that are built into Proteus. And the way you can access some of these is to go under File and then open a sample project. And in here, there are a plethora of different projects. Okay, so for example, if we look at our oscillators, let's say graph-based simulations, this is great. 741 op-amp model. Let's go for this one. And so here, and this is a great segue back to our plots. You can see that we're able to build up a circuit and simulate the frequency response, the analog analysis, the noise, and the distortion. Very powerful tool and a very good resource. So please do take the time to sort through the sample projects that Proteus does have for you, and they all simulate. So if you want to learn how to connect USB, if you're looking for Internet of Things, there's a bunch of programs and board layouts that are there. If you want to run Raspberry Pi or Arduino, there are so many projects that are built right in. Please take advantage of them and get excited about all the things that you can design, prototype virtually, and then go that step further. If you like this video, please give it a thumbs up. If you didn't, thumbs down's fine. I'd love to hear from you, so comments down below, always appreciated. And if you have any requests for content, do note that as well. Subscribe and hit the bell if you want to be notified of new videos when they become available. And as always, thank you for watching and have yourself a great day. All right. Bye now.